In the last lecture, we started a new topic, work and energy, and we talked about the conservative and non-conservative forces. And to kind of like just do a quick review, we said that for conservative forces, their work does not depend on the paths. So conservative forces, we said that their work is just depends on the initial and the end point of the path, not the path itself. So work does not depend on path. And we said for non-conservative forces, the work does depend on the path. So work depends on path. And we had the equation for the work. So we said that for the work that is done by a force is just the integral of F dot dr, which dr was the displacement vector from A to B. So basically we said that if we have a particle that is moving in a coordinate system, so here let's say that this is X, this is Y, and this is Z, and we have a particle that is just moving on a general path from A to B, so A to B, and the force F is just acting on this particle. So here we have the force F, and we said that here is the integral that gives us the work that is done by the force F. And we kind of like developed a set of equations to kind of like determine whether a force is conservative or not. We basically said that if we have the force of F equal to f of x, which is a function of x, y, and z in the I direction, plus f of y, which again is a function of x, y, and z in the j direction, plus f of z in the k direction, then we had the Cauchy-Riemann conditions to determine whether this force is conservative or not. We said that we just calculate the partial derivative of fx with respect to y and check to see if it is equal to the partial derivative of fy with respect to x. So we had three equations here. Partial derivative of fx with respect to z, partial derivative of fz with respect to x, and then partial derivative of fy with respect to z, partial derivative of fz with respect to y. And we said that these are Cauchy-Riemann conditions. So Cauchy-Riemann conditions. So we solved also example on these on this concept. We said that if one of these equations doesn't hold true, then we can definitely say that the force is not conservative. But if all of these equations are true, and we are able to find the potential function, then we can say that the force F is conservative. And for the potential function, we basically said that, so we have a function which is a potential function, which its differential was equal to force dot displacement. So the differential of this function in general is just the derivative of phi with respect to x dx plus derivative of phi with respect to y dy plus derivative with respect to z dz. If we said that this is the definition of the potential function, that we want to just find a function that its differential is equal to f dot dr. And we showed that how we go after this equation to find f. We basically said that this is going to be fx dx plus fy dy and fz dz. And in order to find the phi function, we just use the derivative of phi with respect to x should be equal to fx derivative of phi with respect to y should be equal to fy, and derivative of phi with respect to z should be equal to fz. And we showed that, we started with this, we integrated the equation, and we got a constant which was a function of y and z, and then used these two other equations to kind of like get insight on that unknown, on that constant function. And at the end we had a constant number in the potential function. So if the Cauchy-Riemann conditions are true and we are able to find this phi function, the potential function, then the force is conservative. So here we want to just continue on this. First of all, we want to have another definition, which is potential energy. So potential energy, which is very, very simple, potential energy. We are going to use energy. We are going to use these concepts for the work and energy principle. That's why we are introducing this. So potential energy basically, potential energy, which oftentimes we show it by U, capital U, is equal to just minus phi. So here we can see that if we are saying that the potential energy is minus phi, we are assuming that potential energy is basically a quantity that is defined for conservative forces. For conservative forces, if you find the potential function, minus of that potential function is going to be the potential energy. So that's a very, very simple definition. So now that we have the definition of potential energy, let's go ahead and see what is the work and energy principle for conservative systems. And by conservative systems, we mean a system that all the forces that is acting on the particle are all conservative. So we kind of like derive this potential and energy principle in a couple of times for more general cases. So we start with conservative systems, and then we go ahead and calculate the state the potential, the work and energy principle for a general system which could have conservative forces and non-conservative forces acting on it. So here's the work and energy, work and energy for principle for conservative systems. So here we are assuming that we have a conservative systems, all the forces are conservative, and we want to calculate the W, the work of all the forces that is acting on a particle. So F total is going to be from A to B, F total dot dr. So because we are assuming that the system is conservative, we are assuming that there is a potential function for this total force that is acting on a particle. So basically I can rewrite this integral. So this is on path C, but because it is a conservative system, that's why I didn't write down C, because the work doesn't depend on the path. So we just use the definition that we had. Because it is conservative, we can find the potential function here, A to B, and this is going to be phi at point B minus phi at point A. But we just defined also the potential energy. We said that the potential energy is just minus potential function here. So I can rewrite this in terms of U. So I can say that this is basically UA minus UB. We will see in a moment why we are doing this. So WF total is equal to, so phi B is minus phi minus UB. So just kind of like bring this term, rewrite this term by writing UA at first. So this is going to be UA minus UB for conservative system, Okay. So this is one equation that we have. Actually, let me see if I can use a box here. Yeah, this is much better. Okay, so this is work and energy principle for conservative systems. Now let's derive the work and energy principle for a general case where we don't know if all the forces are conservative, if they are not. Some of them are conservative, some of them are not conservative. Just in general case. So work and energy principle in general case. So here again we assume that we have a system, we have a particle that the total force of F total is acting upon it, and we want to calculate the work of that force. So F total, this is the sum of all the forces that is acting on the particle. So this is going to be, and right now I'm not assuming that if those forces are conservative, they're or non-conservative, whatever they might be. This is a general kind of like derivation. W of F total is equal to F dot dr from A to B. So here I can write down A to B, and for F, because this is F total, we know that from second law of Newton, F total is equal to ma, which is mass times acceleration. So I can write down this ma dot dr is equal to, and for a acceleration, I know it's just a time derivative of velocity. So I can again rewrite this as integral from a to b m dv dt times dr. So now this dt is just a scalar quantity. I can bring this to the denominator of dr. So I can also go ahead and write down a to b m dv dot dr over dt. But this is v, dr over t dt, that's the definition of velocity. So this is basically a to b m dv dot product v, which is equal to. Now I would say that, so I can just kind of like change the order of these terms. I can write down mv dot dv because the order doesn't matter in the dot product. So I can basically write down this as a to b m v dot dv. Probably now you can guess that where I'm going with this. So I can also say that, so here I write down an equation, and after I'm done with this, I prove that equation. So I would say that v dot dv, so these are all two vector quantities, their dot product, which is going to be, the dot product of two vectors is going to be a scalar. I'm saying that this quantity is equal to the absolute value of v, the magnitude of velocity, times d of the magnitude of velocity. I will prove this. But if we assume that this equation is correct, I can go ahead and further simplify this equation. I can say that Wf total is equal to a to b m v dv. So now this is an integral that we can calculate. This is basically m magnitude of v squared over 2. So we have m magnitude of v squared over 2 from a to b, which is going to be Wf total is going to be m v b squared over 2 minus m va squared over 2. So we show that the work of all the forces that is acting, the sum of all the forces that is acting on the particle is equal to this quantity, mvb squared over 2 minus mva squared over 2. But you can see that this is just the kinetic energy. So this is the definition of kinetic energy. So for kinetic energy, kinetic energy, we show it by T. It's just, by definition, it's just mv squared over 2. So I can now say that this equation is basically TB, kinetic energy at point B, minus T, kinetic energy at point A. So WF total in general is equal to TB, or we can say T2 minus T1. So B was the end point of the path and A was the starting point. So it's better to just write down T2 minus T1. So that's basically TB minus T1. This is basically 1 over 2 m V2 squared minus V1 squared. So this is work and energy principle just in general. We didn't make any assumption on the type of the forces that is acting on this particle. So now I have to just show that equation that we assumed here, v dot dv should be equal to the magnitude of v times d, the differential of the magnitude of v. So that's very simple. So here we just say that so v dot v, I can write down this, v dot v is equal to v squared. So the dot product of a vector by itself is just its magnitude squared. Now I can take differential from both sides of this equation. This turns out to be v dot dv plus, or actually dv dot the derivative of first one dot the second one plus the derivative of second one dot the first one. So here basically doesn't matter, the order doesn't matter. So here dv dot v plus v dot dv is equal to, and the differential of this term is equal to 2 magnitude of v dv. So dv dot v is equal to v dot dv. So basically here I can write down 2v dot dv. So 2v dot dv is equal to 2v dv magnitude. So I can cancel out the 2's here, and we have v dot dv is equal to the magnitude of v times the differential of its magnitude again, v magnitude of v again. So this is what we wanted to show. So now we have the work and energy principle just for a general case. So the work of all the forces that is acting on the particle is equal to its final kinetic energy minus its initial kinetic energy. Now we can actually combine these two equations. We can use these two equations that we obtained, one for conservative systems, one for general here, and again just write down the work and energy principle for conservative systems here using this concept of kinetic energy. So I can say again here, as I said, we are going to just derive the work and energy principle just over and over for a more general case. So here again, just going back to conservative systems. So we had WF total is equal to UA minus UB, or basically U1, remember A was the starting point, U1 minus U2. That's for conservative systems. So this was for conservative systems. In general, we have WF total is equal to T2 minus T1. Now, if the system is conservative, I can just substitute this T2 minus T1 here. So if the system is conservative, so for conservative systems, we have WF total is equal to T2 minus T1. This is true in general, and for conservative system, this is also equal to U1 minus U2. So from here, I can just use these terms here and bring U1 here to the left hand side, or actually bring T1 to the right hand side of the equation and bring U2 to the left hand side. So this would be T2 plus U2 is equal to T1 plus U1. So what is this equation is telling us? So this is basically saying that this is kinetic energy. So kinetic energy, and this is potential energy. So this is the kinetic energy at point 2, potential energy at point 2. Same thing here, kinetic energy here, and potential energy here at point 1, point 1. So this is basically the equation for conservation of energy. So this is basically conservation of energy. So it is telling us if the system is conservative, all the forces that are acting on the particle, they're conservative. Then we have the conservation of energy. The kinetic energy plus potential energy at the end point is equal to kinetic energy plus potential energy at the starting point. So if we just show that energy with T plus U, here we are getting E1 is equal to E2. The energy of the system doesn't change when it goes from point A to point 2 if the system is conservative. So this is again a very, very useful concept in just solving problems. If we have a system that is conservative, then we can basically write down the conservation of energy for it and then kind of like find the unknown quantity in the problem. So again, let's just go one step further and derive the work and energy principle again for a general system. So again, work and energy principle. So we derived an equation for this for a general case, but we want to kind of like expand on that equation a little further. So for a general system, so this is a general case. General case. If we don't know that all the forces are conservative, all we can write down is that F total is equal to T2 minus T1. That is, we show that this is true whether the forces are conservative or not. So I can also divide the forces that are acting on the particle in two groups, one conservative forces and one non-conservative forces. So basically here I can say that this W is equal to the work of all conservative forces plus the work of all non-conservative forces. It's equal to T2 minus T1. We just showed that the work of all conservative forces is equal to U1 minus U2. So I can rewrite this term using the equation that we had for conservative systems. So I can say that this is equal to U1 minus U2 plus work of all non-conservative forces. So non-conservative forces is equal to T2 minus T1. Now if I bring this potential term, these two potential terms to the right hand side, we're going to have W of non-conservative forces is equal to T2 plus U2 minus T1 plus U1. So this is basically the energy at the end of the path, at the end configuration. So this is basically E2 minus E1, and this is energy at the starting point. So here we are saying that the work of all non-conservative forces is equal to the difference in the energy of the system. If this quantity turns out to be positive, E2 minus E1 turns out to be a positive, that means that from going point 1 to 2, the energy of the system has increased, and the work of all the non-conservative forces is a positive quantity. That means we have kind of like pumped energy into the system. If this term is negative, that means that the work of all the non-conservative forces is negative. We have dissipated energy from the system. So this is basically the work and energy principle in a general case. So it is true for all the systems, whether they are conservative or not. So with this being said, I think we are ready now to solve few examples. So let me write down this. So if the work of all, if W non-conservative is greater than 0, then we have pumped energy into the system. Pumped energy into system. If this quantity is negative, then we have dissipated energy. Dissipated energy from system. So with this equation, now let's just go ahead and solve a few examples. Here is the first example that we want to solve. I paused the video to just draw this example so that we can save a little bit of time. So we have a slider that is attached to a string, and we are pulling that string with 400 Newton force here. And that slider is connected to a spring, and it is sliding over a kind of like half a circle path. We are giving the slider an initial velocity of 10 meters per second, and the problem asks to see how high the slider would go, what is the theta maximum basically here, and also the question asks for the velocity of the slider as a function of theta. And we have all the quantities that we need to solve this. The constant of the spring is 300 Newton per meter. The initial length of the spring is 1.5 meter, and the radius of the semicircle is 2 meter. So, and here this string is just kind of like attached to this pulley that its radius is kind of like negligible. So this is basically, this pulley is just center of this semicircle, and we are assuming that the motion of this slider on the semicircle has no friction, so we don't have any friction in this problem. So after solving, this is the first example that we want to solve with work and energy, but after solving few examples, you kind of get a taste of what problem is a kind of like work and energy problem, and what problem is kind of like conventional Newtonian problem in a sense of that you need to use F equal ma, just sum up all the forces and derive the acceleration. Here I want to use the work and energy principle to solve this. So for the work and energy, to use the work and energy principle, first of all, I need to determine whether the system is conservative or not. We have an equation for conservative system that is much easier. So if we have a system that we identify as a conservative system, it's basically better to use that equation, which is basically the conservation of energy. But if the system is not conservative or we are not sure, the best option is always to go with the general format of the work and energy principle. Here, the forces that are acting on the particle, we have three forces that are acting on the particle. One is a spring force here, which is a conservative force, and I leave that to you guys to show that the spring force is a conservative force. We have force of gravity, so in this problem we also have gravity. This is the direction of gravity. The force of gravity is also conservative. Also, you can show that, very, very simply, kind of like by using the Cauchy-Riemann conditions and finding the potential for the gravity force. So these are the two forces that are acting on the particle, the spring force and the gravity force, that we know that they are conservative. But about this 400 Newton force, we don't know if it is conservative or not. So I'm going to just assume that this is non-conservative. Basically, in all the problems that we have, the only conservative forces that we assume are spring forces and gravity. So aside from those two, all the other forces, we treat them as non-conservative and calculate their forces basically. So I would say that the W of non-conservative forces here is equal to, we just derived the equation for this, is equal to T2 plus U2 minus T1 plus U1, which again, T is kinetic energy, U is the potential energy. So let's calculate T1 and T2 first. So for T1 here, because we have given the initial velocity of 10 meters per second to this slider, we can easily calculate the T1 here. So T1 is equal to 1 over 2. Oh, by the way, we need the mass of this slider. So the mass is 5 kilogram here. I forgot to write that down. So M is 5 kilogram. So the kinetic energy is equal to 1 over 2 times mass, which is 5 here, times velocity squared. So here 10 squared. So basically this is 100, 500 over 2, this is 250. And this dimension is joule. That's the dimension for energy. Or you can substitute kilogram times meter per second squared. So that's T1. What is T2? Well, because we are asked to find the velocity as a function of theta, let's assume that this particle, this slider, is at position of theta with the unknown velocity of v theta. So I would say that T2 is equal to 1 over 2 times 5 times v squared, which v here is a function of theta. So v theta squared. And I don't write down the kind of like the vector symbol and also the magnitude symbol here, because we know that by this v squared we mean the magnitude of the velocity vector. So when the slider is moving here, it has both kind of like horizontal and also vertical velocities. And by saying that v squared, we mean just kind of like vx squared plus vy squared. This is kind of like the magnitude of the vector velocity squared. So that's T1 and T2. What are U1 and U2? So we said that we are gonna just, in all the examples, we are only gonna treat gravity and spring as conservative forces. So U1 here, I would say that is equal to U1 spring, or just U spring plus U gravity. So what is the potential energy of a spring? Again, I think we actually derived the potential energy for a spring. I'm not 100% sure, but you can easily derive the potential energy for a linear spring, or even potential energy for gravity. For a spring, we know that the potential energy is just 1 over 2 k times delta, kind of like the elongation of the change in the length of the spring squared. So this is basically 1 over 2k, let's say that delta L squared. And this is basically the end length of the spring minus its initial length. Here is just L0 at rest this spring. Plus, actually this is delta L, this is the kind of like change in the length of the spring from its rest position at point 1 here. And because we have assumed that this is the rest position, so L0 is just a kind of like the rest length of this spring. There is no force in this spring when the slider here at the beginning of the motion. So because of that, delta L would be 0 basically, because the length of the spring minus its initial length is equal to 0. L0 minus L0 is equal to 0. So this is the potential energy for a spring, and for gravity we have mg, again delta H, or I can consider this kind of like bottom position here that we have this for the slider as the reference for gravity. So this is basically, that doesn't turn out good, but you get the idea. So this is kind of like reference for gravity. Reference for gravity. So because we are at the reference here, basically there is no kind of like potential energy due to gravity. I can say delta H here, and again H here, delta H means the height at this position minus the height of the reference position, which is equal to 0. So this is basically 0 plus 0 equal to 0. That's U1. So when the spring is just at rest position, it has its rest length, and we are at the reference of the gravity for the potential energy due to gravity. We don't have any energy here for the slider. What is U2 here? So if we go ahead and say that U2 again has a spring component plus gravity component. So here we have to calculate the length of the spring here when the slider is at position theta here. So basically we need to find this length here. So when the slider goes here, this is the second kind of like the end length of the spring, the length of the spring at the second position. So we have to find this, and in order to find this we can kind of like use kind of like geometry here to find that. So here basically we have, maybe it's better to kind of like draw the triangle here. So that's the length that we are looking for. We have a triangle like this, and this is basically, this goes to the center of the circle. So this is R, and again this is L0. Oops. So this is L0, and basically here again this is R also. So this quantity is also R, because the kind of like the slider is moving on a semicircle path here. So that's the semicircle, and these two lengths doesn't appear to be equal here. This one is a little longer, but you get the idea. This is R and this is also R. So this is the initial length of the spring. We are looking for this side of this triangle. So I can say that, let's change the color. I can say that if this is theta, this quantity, this is theta. So this quantity here is R sine theta. So this is basically r sine theta. And therefore this length here is just r sine theta. And for this side here, so the whole thing here is just r, and this part is just r cosine theta. So this side would be r minus r cosine theta. So this would be r minus r cosine theta. So now I have a triangle that I have this side. It's a right angle triangle. We have one side here, we have one side here, so we can find the second length of the spring here. So we can say that here this is equal to, again, 1 over 2 k delta L squared plus this is mg delta h. So this is equal to, so this is delta L, this length is equal to delta L. So what is delta L here? So this is basically delta L. So delta L is equal to, it would be a square root of this side squared plus this side squared. So it would be L0 plus r sine theta squared plus r minus r cosine theta squared. Actually, we are talking about delta L, so it would be the second length minus its initial length. So this would be minus L naught. This is basically L2, so let me correct this. So this is L2. So basically L2 minus L1. So that's delta L. And for delta H here, so because here this point was reference, the slider has gone upward here with the value of r minus r cosine theta. So delta H is r minus r cosine theta. So we have U2 is equal to 1 over 2 times k times delta L squared. So it would be this quantity L0 plus r sine theta squared plus r squared 1 minus cosine theta squared minus L naught squared plus mg delta H, which is here r 1 minus cosine theta. So that's the potential energy when that angle is just theta, when the slider has gone up such that this angle is theta, and so we found the potential energy at that point. So now we can use the work and energy principle, because now we have U1, U2, T1, T2. I can say that the W of non-conservative forces is equal to, so U2 plus T2 minus U1 plus T1. So here U2, we just calculated this would be 1 over 2 k, and I'm not going to write that equation again, so I just use delta L squared, but we know that this is a function of theta, so maybe it's better to just write down delta L of theta squared plus mg r 1 minus cosine theta minus U1 and T1. So we had T1, it was, I think, 1 over 2 times 5 times 100, which was 250. So minus 250. So minus U1 was 0, 0 plus 200 of 50. So now we have to calculate this, the work of the non-conservative forces. And here it's very easy to calculate the force because, so you can see here that the 400 Newton is just a kind of like the tension in the string. And because this string is always kind of like going toward the center of this semicircle, so this line always, the string would always be kind of like normal to the tangent, to the circle, to the semicircle. So because the displacement is always tangent to the path here, so we have the displacement tangent to the semicircle. This line, which is our force, is normal to the displacement. We know that when the force is normal to the displacement during all this path, the force is always normal to the displacement. When the force is normal to the displacement, the work of that force would be zero because the work is kind of like F dot dr, the dot product of the force and displacement. So here we would have F dot dr, we should integrate this, is equal to this quantity that we wrote down. Okay, so these are vector quantities. Delta L of theta squared plus mgr 1 minus cosine theta minus 250. Because these two quantities are these two vectors are normal to each other, so here this would be 0. It's equal to, again, the same thing here. Let me see if I can copy and paste this. So I think I can move it, but I used to be able to copy this, but anyway, I can just rewrite it. Or just leave it here, just same thing over here basically. So same thing over here. So now we have an equation for theta. We have an equation actually for v theta. So because I think we dropped one term here, the kinetic energy. We dropped the kinetic energy at the second point. So I should also add that. So that would be here plus 1 over 2 times 5 times v theta squared. So it's better actually to write this again. So here we are gonna have 0 is equal to 1 over 2. So this here again we have plus 5 over 2 v theta squared times k, and k was I think 300 times 300 times delta L of theta squared plus mg, or we can substitute g, we can substitute 10 for g here, or just leave it as mg. So mgr 1 minus cosine theta plus 5 over 2 v theta squared minus 250. So now we have an equation actually for v theta. We can find v theta from this equation. So v theta is equal to square root of, we have to bring this term here, 250. Let's bring the 250 to the left side. Minus, here we have 150 delta L squared. This is a function of theta. Minus mgr 1 minus cosine theta. And everything should be multiplied by 2 over 5. So basically a square root of this quantity. This is v theta. So that's the velocity of the particle as a function of theta. And we want to also see how high the particle would go. So we want to see if we give this initial velocity to the particle, how high on the semicircle the slider would go. So if we are looking for that point, we know that at the end point, if the particle goes up until its maximum, the velocity at the end point would be 0. So it's just it is enough for us to this we can just substitute v theta equal to 0 into this equation, and that's enough. We get a kind of like an equation for theta, and that theta gives us the theta maximum, the maximum height that the slider would go. So if v theta is equal to 0, then theta would be equal to theta max. So that's basically kind of like an algebraic equation. This is how kind of like treat work and energy problems. It's just we write down the work and energy principle here. As I said, we just treat the spring force and gravity force as conservative forces, and treat all the other forces as if they are non-conservative, and just write down the work and energy principle in this format. You can find the unknown, which here it was v theta. So this is for the first example. This is another example that we want to solve. So we have two sliders here, A and B, that are connected to each other with link AB. So slider A has a mass of 3 kg, is connected to a linear spring with a constant of 300 Newton per meter. And slider B has a mass of 2 kg and has an initial velocity of 20 meters per second. The length of the link AB is 4 meters. The gravity is in this direction. The acceleration due to gravity is 10 meters per second squared. We don't have any friction, and also the spring is at rest here. So this is the initial length of the spring. There is no energy stored in the spring at this moment. So we want to find the velocity of slider A and B, and also figure out how high the slider B would go because of this initial velocity. So basically this is like kind of like giving an initial velocity to this slider, like for example hitting it with a hammer to just go in the upward direction. And because this is connected to a spring, so the motion of this slider would be limited. This just goes up to a certain point, and then just starts it would start going downward. So this is kind of like the physics of the problem. So let's start with the work and energy. Because here we don't have any friction, and we have only the gravity force, the force due to a spring, and also we have the normal forces of these surfaces, the two surfaces that the sliders are rolling on them. Those are two kind of like reaction forces from the surface, but they are always kind of like normal to the direction of motion. So this slider is moving in the horizontal direction. The normal reaction of the surface is in the vertical direction. So the work of that force is equal to 0. And the same thing is true here. This slider is just moving upward and downward. So the reaction force of this surface is in the horizontal direction. Because it is normal to the direction of motion, it is always normal to the direction of motion. Its work is equal to 0. So basically, because we don't also have any friction, here we have kind of like the conservation of energy. This is a problem in that category. So here we would just say that T1 plus U1 is equal to T2 plus U2. Or you can start writing down the W of non-conservative forces is equal to E2 minus E1. Energy, both kinetic and potential energy. And then argue that the W of non-conservative forces are 0 here. So we have the conservation of energy here. Let's calculate these quantities. So at the initial position here, where we have this 20 meters per second velocity for particle B, for slider B, the spring is at rest, we have to calculate the kinetic and potential energy. And then we just assume that this slider would go up by an unknown value, let's say y, and then calculate the kinetic energy and potential energy at that unknown position. and then we should be able to figure out the velocity of, for example, a slider B and also slider A. This is kind of like a good example. I like it because we have to also kind of like we have to use our knowledge from kinematics here. So you can see here that the velocity of A and B are related here. They are related to each other, and we should use that equation. So let's start from T1. So here T1 would be TA plus TB, the kinetic energy due to all the masses in the system. We are assuming that the link doesn't have any mass. So what is the kinetic energy of slider A? Well, we have to figure out its velocity. We have the velocity of slider B, so I can write down here TA plus 1 over 2 mb VB squared, which we have all these numbers here, mb, the mass of slider B, and its velocity. But for TA, we don't have its velocity, but we should be able, by having the velocity of this point, of this kind of like rigid body system, we should be able to figure out the velocity of this point. So here the easiest way to kind of like to calculate the velocity of point A, so there are actually two ways, just basically same thing, but kind of like two approaches to calculate the velocity of A. We can say that, okay, write down the velocity of point A based on point B. We would have omega, the angular velocity of this link, showing up in that equation, which is an unknown, and then force VA to be only in the horizontal direction. Then we should be able to find omega and therefore find velocity of A. Or I can use the concept of instantaneous center of rotation. So here, for this system, I can basically say that because we have, this is, let's say this is point A, it is going in this direction, its velocity is an unknown quantity, but it is in this direction, in the horizontal direction, and I know it's kind of like to the right because particle B is going upward. So we know that the instantaneous center of rotation for this system, it should be normal, it should be somewhere on this line that is normal to this velocity, VA. Also, I have the velocity of VB here. We know that the velocity of VB is in the vertical direction, so the instantaneous center of rotation here should be also somewhere on this line, normal to this velocity. So basically, this is the instantaneous center of rotation. So this is IC. So let's call this O, and we know that this is basically 4 meter here. We have AB 4 meter, and we also have this angle. So we can write down VA, let's write it here. VA is equal to OA times omega, and VB is equal to OB times omega. So if we divide these two equations, so VA over VB is equal to OA over OB. The omega, they would cancel out. So now we have VA over VB is equal to OA over OB. But what is OA over OB? So this is basically OA, which is equal to this distance, over OB, which is this distance. So that's 1 over tangent of the 60 degree here, the 60 degree angle that we have here. Or I can write down here, this would be kind of like 4 sine 60, this would be 4, this side would be 4 cosine 60. So this is actually OA, which is that distance, that's 4 sine 60. Here is just 4 cosine 60. So therefore VA is equal to the 4 also, they would cancel out. This is square root of 3 over 2. This is 1 over 2. So this is basically the square root of 3 times VB. So this is the relationship between VA and VB. And here, because at the initial moment we have the velocity of point B, we can write down, we can find out actually the value of VA actually. So here VA would be, so VA1 would be the square root of 3 times 20 meter per second. So let's make sure that we haven't made a mistake here. Oh, that's fine. Okay, so going back to calculating the kinetic energy, T1, remember it was TA plus TB. So let's just substitute those terms. So T1, it is equal to 1 over 2 MA VA squared plus 1 over 2 MB VB squared. So this is equal to 1 over 2. What is MA? I think it was 3 kilogram. Yeah, 3 kilogram, and MB is 2 kilogram. Yes. So this is 1 over 2 times 3 times VA, which is 20, the square root of 3 squared, plus 1 over 2 times 2 times 20 squared. So this is easy to calculate. This would be 3, this would be 400. 400 times 3, that's 1200. 1200 over 2, that's 600. 600 times 3, that's 1800. Plus, here we have 400, 800, and 400. 400. So this is 2200. And we know that the dimension of energy is joule. So that's T1. Let's figure out U1 also. So here U1 also has two components here, one for A, one for B, and for both of them has two components again, one for spring, one for gravity. Because this slider A is just moving in the horizontal direction, so it has really only the spring potential energy. The potential energy is stored in the spring and doesn't have any potential energy due to gravity. And for the second slider, it is not connected to any spring, so doesn't have any potential energy due to a spring, but it is moving in the upward in the vertical direction. So it does have the potential energy due to gravity. And here let's just consider here as a reference here, this line as a reference for gravity. Reference for gravity. This is kind of like arbitrary because you can also consider, for example, here the initial position as the reference for gravity. But if that's the case, you have to also keep in mind that A would be also at some height from reference. But actually, it doesn't matter because the height doesn't change here. So even if we consider this as 0, so actually I think it does matter. So if we consider here as a reference for gravity, then particle A, the slider A, has a negative potential energy due to gravity because it is below the reference line. But the point is that, so when this particle just moves to the second location, again, it is at the same height below the reference point, so they would cancel out. So we should kind of like consider it, but at the end, it would cancel out. But here I just, for simplicity, I just consider this as the reference for gravity. So here for U1, I would say it would be U spring in A plus U gravity in B. So because the spring is at its rest position here, there is no energy stored in the spring here. So UA from the spring is equal to 0. So this turns out to be 0. Plus here, this would be MB G times H, the height of point P from the reference line here. So this is 4, this is 60 degree, so this would be 4 times sine 60 degrees. So here we have mb times g times 4 sine 60 degree. So that's u1. Let's now move to calculate u2 and also t2. So I think it's better to just kind of like highlight this here. So t1, this is t1. Let me draw a line around this. So, and also this is u1. Okay, for t2 and u2 here. So what is t2? So again, t2 would be 1 over 2 m a v a squared plus 1 over 2 m b v b squared. So this is equal to, so here we have to consider that this slider has gone up, by a certain value, by a certain height here. So let's actually draw another shape here. So here, so here these are the surfaces that we have, and here let's say this is AB. So this is AB, and now AB, this was the AB initial position of AB, and now it's kind of like something like this. So, or actually let's use another color here. So something like this. So this is A1, B1, and this is A2, A2, B2. So with that being said, let's calculate the potential energy. So we don't have the velocity of either of these points, but we know that their velocity should hold this equation true, because we derived this, Again, we can do the same thing here. So we can assume that this angle is theta. Actually, the square root of 3, we don't have that anymore. It's just, if we consider this as theta, so we would have kind of like the same argument, but instead of sine 60 here, we would have sine theta, cosine theta. So we have VA over VB is equal to 4 sine theta over 4 cosine theta. This is tangent of theta. So basically, VA is equal to VB tangent theta. Okay, so I can write the kinetic energy as a function of only one unknown here. So here T2 is equal to 1 over 2 times MA, which is 3, times VA squared, which is VB tangent theta squared, plus 1 over 2 MB, which is 2, times VB squared. So this is 3 over 2 tangent theta squared, plus 1 here times VB squared. This is T2, the potential energy at the second moment, at the second position. So let's calculate U2 here. So U2, it would be, again, U spring A plus U gravity B. So let's calculate the energy that is stored in the spring here. So if I go up here, so here when this moves to the right, the spring is going to be a stretch, and we have to actually calculate how much this slider has moved to the right, and from that we have to find the elongation of the spring. So let's say that this length here right now is just 4 cosine 60, and when the slider A goes to the right, this side would be 4 cosine theta. So the elongation of the spring would be 4 cosine theta minus 4 cosine 60, or actually 4 cosine 60 minus 4 cosine theta. So basically, let me go to this shape here. So we have this is equal to 4. Let me erase this A2 here. This is A2. So this length is 4 cosine 60. And this length here is 4 cosine theta. So this is 4 cosine theta. And this length here is just the elongation of the spring, which would be 4 cosine 60 minus 4 cosine theta. So we can write down here, this would be 1 over 2 k times 4 cosine 60 minus 4 cosine theta squared, plus the potential energy that is stored in B due to gravity. So again, we can do the same thing here. So this is 4 sine 60, and this is 4 sine theta. So I can say that this change in the height would be, or actually because we are just measuring everything from here, this would be 4 sine theta, because for U1, remember, for U1 here, we put this is 4 sine 60. So because we are measuring the height from this reference position, we have to put this value here, not just a change in height here. So this would be, now at the second position, it would be 4 sine theta, this value from the reference line. So we would have B, so we would have BG times 4 sine theta. Okay, now we have T1, U1, T2, and U2. So here, and now I can use the conservation of energy. Say that T1, which was, I think, 1800, we calculated that. So 2200 actually, so T1 plus U1, so here T1 plus U1 is equal to T2 plus U2. So we get from this 2200 plus U1. What is U1 here? You calculated this. This is basically MB, which is 2 kilogram times G, 20 times 480 times sine 60, which is a square root of 3 over 2. So that would be 40 square root of 3. So 40 square root of 3 plus T2 plus U2. So we have T2, which is, bring this a little down. So this is 3 over 2 tangent theta squared plus 1 times VB squared plus U2, which is this quantity here. So this would be, we have also the constant of the spring. I think it was 300. So yeah, it's 300. So this would be 300 over 2, that's 150. 150. 4 cosine 60. We can bring actually 4 out, so that would be 16. So I can write down here times 16 times, this is cosine 60, which is 1 over 2 minus cosine theta squared plus, so this was actually equal, not, so T1 plus U1 is equal to T2 plus U2. So this is equal to, and this term, so here we have MB times G times 4 sine theta. So MB is 2 times 10, that's 20, times 4, that's 80. So this is 80 sine theta. So now this equation has only, has two unknowns basically, VB and theta. But here we can find VB based on theta. So that's what we were looking for. We wanted to find the velocity of A and B as a function of theta. And from this equation, we can find VB as a function of theta. And because VB and VA are related to each other, we can also find VA. So here, to kind of like simplify this, this would be VB, it is equal to, so 2200 plus 40 square root of 3 minus, so this would be 2400. 2400, yes, times 1 over 2 minus cosine theta squared minus 80 sine theta over 3 over 2 tangent of theta squared plus 1, and the whole thing should be inside square root. So this is VB, and now that we have VB, let me check that if we have done this correctly. I think it's correct. So now that we have VB, so VA is basically, I think, tangent theta times VB. Yes, so VA is just basically tangent of theta times this quantity times VB. So if we want to find the theta maximum, or actually how high the slider B would go, so here as a slider is going up, this slider is going to the right, this angle is just increasing. So at the end, when this slider B reaches velocity of 0, that angle, the theta, would be maximum. So, and based on theta maximum, we can determine how high B would go, the slider B would go. So here, it's just to find theta maximum, if we put here from here, if we put VB equal to 0, and we should be able to find theta maximum. Theta, oops, my pen is acting up, so theta, put VB equal to 0, and theta maximum would be found from this equation. It's a kind of like trigonometric equation, and we are not looking for solving this, but the idea is important here. So that's how we find the theta maximum. We found the velocity of B and also A as a function of theta, and we also know how to find theta maximum, or the highest value that the slider B would go. So I think with this example, this is good for this lecture, and I guess I see you guys in the next lecture.